Hi everyone. Today I want to talk about resonance. So should I would say repeat. So because this topic bridging between an advanced rate level of mathematics and physics and advanced topics of recent research areas. I mean, non-Hermitian, water and the distributive systems. So I want to start from the quite easy mechanical intuition. So at first, we consider some kind of particle or wave, and that number is given. So then we consider some physical system, and we observe scattering and cross section. This is a very probabilistic meaning. So then, typically, for example, I want to focus on total potential. So this is quite often happens in our stellar universe. So then, but here we can see the kind of thresholds. So below this threshold, we can observe discrete spectrum. This is quite good observation at maybe 100 years ago. So, and also we can see the continuous spectrum of scattering problem. So that the bound state is localized to this region because of this potential. So now we can consider this kind of potential. So the symmetrically flat potential. So then there exists pseudo-bound state. So at first we consider again wave or particle coming with particle. So then some physical phenomena happen, but we can observe transmission wave, scattering wave. But now in this case, we can observe apparently temporary bounded phenomenon. So then, actually, this is the discrete spectrum. So then, we can see some energy spectrum. Now, this is not real. So this is a complex E-plane, energy plane. Now, this is the imaginary part of energy. So this is a discrete states at discrete point, and this has a complex energy, and this means the decay rates of the system. So this means the system is unstable, discrete, and complex energy. So this phenomenon is said as resonance. So in this case, especially quantum resonance. So traditionally, maybe more than 50 years ago, so we consider this resonance as a poor singularity of S matrix. I mean, S matrix means transmission. So the transmission probability has a peak at the resonance. This is a quite traditional picture. And second, this is quite mathematical. The mathematicians define this resonance as a resurgent, so-called resurgent. So this is a Hamiltonian. So then this Hamiltonian minus z over 1 over Hamiltonian minus z is called resurgence. So now this operator is well defined or not? Actually, at origin, energy is real. So this parameter z is taken as real number, but we can consider the analytical continuation. So then, at this energy, this operator becomes ill-defined. So this operator encounters singularity. This is a mathematical sense. Okay, so then at first I said I mentioned this as should bound it or temporarily bounded. So I want to ask whether this is physical state, physical wave function. Library, this transmission wave is given by this kind of plane wave, exponential ikx. But now this wave number becomes complex because the energy has a complex number. So then this has this kind of exponential growing factor. So then this function diverges in the naive sense. So actually there is no wave function in this sense. But we can say this is state because of physical phenomenological regularizations. Why such regularizations well defined or well behaved? So now consider the complexification of the coordinate. So this is quite related to the non-Hermitian quantum mechanics. At first, let's consider the Hamiltonian is Hermitian. So then, the Schrödinger equation is the eigenvalue problem. So then the energy is real, just real. So usually, we consider the bound state in this word. So this coordinate is real. So this is coming from minus infinity to infinity. So I say this path is Cp. Now, at resonance, I already said the wave function diverges. So this region is quite singular. So the separate regularizations of a resonant state means exclusion of this singular part. So now I can write this kind of path. I say C R. So I say so some by using, for example, resurgence theory. So we can observe some kind of good convergent path. But anyway, so yeah, we can use other regularization. Then the wave function becomes convergent some kind of function. So then for the bound state, the wave function is meaningful because this square integration is finite. And then naturally this provides the real energy. On the other hand, resonant state now resonance state is well defined on CR. So then this integration becomes finite. But this path is quite complicated. Here is complex explained. So this is quite naturally having complex energy. And also this is in this sense, this is just bound state. So both bound state. At first, I said this is Hermitian quantum mechanics, but actually ill-defined as usual this coordinate. Even if sorry. So if there exists the resonant force singularities, this is quite ill-defined. So then we should take this kind of complex side path. So now some people can consider this path as a one parameter family of a real parameter. And this real parameter is regarded as a coordinate. Then the choice of this path means the parameter space of non-Hermitian quantum mechanics. So at first, Hamiltonian is some kind of Hermitian, and but the coordinate is complex. But on the other hand, here Hamiltonian is not Hermitian, but the coordinate is real. So quantum resonance is quite well defined in this sense. But actually, maybe in this case, so many progress happens in quantum, non-Hermitian quantum mechanics. And actually, there are many subtleties that is quite physical and mathematical sense. So actually, if there exists this kind of Hermitian Hamiltonian, we can define non-Hermitian quantum mechanics quite well. But many non-trivial phenomena was present researches fields. So actually, so if there exists no this kind of Hermitian operator, then actually there's no well-defined mathematical background of the non-Hermitian quantum mechanics. So, but we don't know that if such a Hermitian operator exists or not. So anyway, so this is quite universal phenomenon for the open and the distributed systems. So so the quantum resonance, transition quantum resonance is good. It's good starting point to consider the non-Hermitian quantum mechanics. This is my message. Yeah, thank you.
Also, is your clear review of this phenomenon. So now we take question from young non-experts. So questions. Young, so senior research scientist is senior. Is that scientists and postdocs researchers are
Yeah.
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 Yeah. Yes, yes. Okay.
I thank a very nice talk. Actually, a question regarding the rate cut. It seems you are trying to interpret the resonance as a kind of non-submission system. I think for the rate cut, I really understand. So, for instance, if you so because is this correct? You want to find an equivalent description for in the non-Hermitian system for the red. Is this correct?
Yeah, so if there is this kind of feature,
This part I think that yeah I can understand. But
yeah, so if there exists this kind of your real world, so then the quantum resonance is yeah almost identical to Hermitian quantum mechanics.
I think it's very similar to quantum complex scaling. That's your
Complex scaling. Complex scaling is the a kind of non-unitary transformation of one system. So then the system becomes Hermitian. But we can connect the original this Hermitian system. So this is quite important point. If there exists such a transformation, so this is quite well behaved. But the truly Hermitian case, so this is quite subtle. I'm not sure. So then actually in dimensional Hilbert space case, so then the many phenomena is quite subtle, transferring and physically subtle. Even in the current understanding.
Thank you. Are there any other? Yes.
He said non expert, so well, thank you for the talk. I understood nothing. So I wondered if you could just explain again maybe what quantum resonance is. Like what are you studying? What's the phenomenon you're interested in? Great.
Actually, so at first sight, is quite not part of the phenomenon. So this.
So I already don't know what that is. But very basic. I assume like lots of the non-physicists get my thought. Yeah, not much about this.
So okay, so actually.
So is it like I guess in quantum mechanics you speak about
So the quantum mechanics really is the well-defined theory by mathematician, but this is a quite limited sense. So actually, so so far we success we can many success for results that is the experimentally is widespread.
Yeah.
But recent hot topic is quite actually weird. So that is not supported by mathematicians. But this is calculated naively by using this well-defined quantum mechanics. So many results we can obtain, but that is quite non-rigorous.
So there is the phenomena you can't explain.
Yeah. So true non-rigorous. So
what kind of phenomena?
Huh?
What kind of phenomena?
So for example, the how to say, the usually we consider the Hamiltonian is a square matrix, but in a non-Hermitian case, so this can be rectangular.
But that's not phenomenon, essentially.
So yeah, this is just a linear algebraic
Yeah.
picture. So then this happens many physical subtleties, but this is that know this phenomenon and good backgrounds.
I think the question is if the concept system is open, such no permission cognition in that case.
And the math is insufficient.
Yeah.
Thank you.
Yeah, thank you very much for the good question. Yeah, any other naive question?
Yeah, please.
Yes, please.
I'm also the one who doesn't quite understand the picture. So you introduced the concept of complex energy, and what is that? Is that a real thing? What are complex energies? How do you observe complex energy?
But this is
I think you talked us about the complex energy.
experimentally.
So what are complex energies? You told us about complex energies, but I didn't.
For example, we will put this as a decay rates or as other
Oh, I
singularity.
thought energies are real things, but you told us about complex energies. So what are complex energies?
Complex energy. So this is just real part is energy and but the imaginary part is decay rates. So I mean this is a kind of lifetime. So this bound state.
So how is it defined? How is a complex energy defined?
So usually we observe this as a just poking or scattering in this.
I mean, you how do you observe a complex quantity? How is the imaginary part of E defined?
Yeah.
Yeah,
Yes.
his question is why imaginary part of energy is interpreted as decay, the lifetime of the particle.
Oh. Oh.
Or maybe if you could write the definition of complex energy, then that.
Very simple question. Suppose E is just a complex number, and we consider exponential of IET, right? And when E has an imaginary part, it's E exponential minus something, and it expresses the decay of that value.
Writing down the high matrix and operate it.
Yes.
Yeah.
You
can have it.
Yes, exactly.
Yeah.
That's not this.
Yeah. Actually, this becomes energy, and this becomes time, and energy becomes energy is complex. So we have this kind of exponential damping function. So this means the wave function is becomes not the norm of wave function smaller. So this is the dissipative phenomena.
maybe around 290 or something. Exactly.
So you can talk later.
Yeah.
Okay, okay. Yeah, thank you very much for the good question. So any other naive question? Yes, you have.
Yeah, thank you for your nice talk. And there are many resonance in QCD, but QCD is quantum thermodynamics. But the Hamiltonian of QCD is Hermitian. So can we use the language of the non-Hermitian Hamiltonian to study the resonance in QCD? Can we do this?
Of course, so yeah, maybe there is this kind of yeah, potential to locally, I think QCD, but yeah, QCD is too comparative. So I'm not sure this. I'm not sure this.
There are unstable logic.
Yeah, of course, there exists.
Yeah, but I think in quantum field theory, there is not the concept of the potential when the particle moving very fast.
I'm not sure about the effective function. And this is what it is. So yeah, but in a heavy, for example, in a heavy particles, then you can such a particle of this kind of structure, so then it's also resonance. So yeah, that is quite saying.
Yeah, thank you. Okay, yeah, thank you very much. So now, question from experts and all are accepted.
Well, then,
yes, please.
no expert question. Maybe you may think that the time dependent. Somehow you start doing the X dependent, that's the time dependence. And one of the questions, maybe is if you consider time dependence. And then, in the old days, complex codes should appear in the lower half plane or upper half plane, and so on. That means wave packet will not increase indefinitely, but eventually decrease or go to zero. That's the condition in the part of the complex energy plane analysis.
Yes.
But you said rigidity. Therefore, my question, my interest is that what happens if we have the localized state? Often in the field theory, we put everything in the box, you see. But so actually not normalized, but we discuss inside the box. Therefore, in a case also, wave function may not be normalized, but you put it into some small box, and then you may do some interesting physics. That's my nice question.
Yeah, so then some dynamic limit is quite something. Or this picture is quite something.
Well,
Actually,
that picture essentially easy to
yeah, actually,
special, right?
yeah.
But my question is inside the small box.
Sorry, but yeah, actually, the particular picture is quite not defined. So actually, there is no Fox space at the asymptotic region. Actually, so then at the boundary condition has many non-trivial information. So then if we volume limit this is key.
But still,
Information is
you may get some interesting physics or no. That's my question.
Yeah, so IR physics has well, not really.
Of course, it's true that if you consider only the normalized state, then you may have the very good notion of the asymptotic state and so on.
Yeah.
But my question is that not normalized state, but in a confined region, and that may be physically sensitive or not.
No.
Well, it's okay.
Yeah, no. Yeah, actually, actually, yeah. So, if you consider, even if you consider quantum mechanics, then so the actually asymptotic form of the wave function is not very defined, even if the Coulomb potential or other Coulomb or polar potential actually. So the we don't know that analytical structure of the system.
Well, in the past, we consider mainly the Hermitian Hamiltonian. But nowadays, many people discuss non-Hermitian Hamiltonian.
Yeah.
Therefore, in the same speed, I was asking whether you can explain something
Yeah. So
normalized or not normalized.
Yeah. There are many problems actually. So, but the physicists don't care, but just use the traditional technique.
Thank you. So that's the question from this group. You have? Yeah,
Please. So can I ask something about the normalization? So on the complex quantum part, I think it's okay, but can you define probability density at some real point X?
No.
I think that's really a problem of non-Hermitian deforming integration factor.
No.
Oh. Also that's the open question.
Yeah.
Okay, thank you.
Okay, thank you very much. So any question from the Zoom audience? If you have, could you unmute yourself and speak up? So if not, let's thank Morikawa-san. Thank you very much for coming.